Hi everyone! In the previous videos, we began to develop a notebook to analyze a large CSV of temperature data. We also started the implementation of a new data structure called parList that should eventually run computations in parallel. We stopped after implementing mono-fold-left, a limited version of fold-left where we squash all the data inside the collection without changing its type. In this video, we'll try to find out how to analyze a dataset efficiently using mono-fold-left. Let's have a look at one of the simplest functions that we implemented in the previous videos. For example, a sum temperature. It takes a parList of samples and returns a double, representing the total temperature. How can we re-implement this function using mono-fold-left? If we called mono-fold-left on the input parList, we would need a monoid of sample, and it would return a sample, not a double. This means that we need to apply some transformations, either on the input parList or on the output sample. I'll let you think about it for a couple of minutes. Please pause the video and try to refactor sum temperature using mono-fold-left. Let's have a look at this diagram. We know we can't transform a parList of samples into a double using mono-fold-left, because this function doesn't let us change the type of the elements inside the parList. However, if we had a parList of double representing the temperature for each sample, then we could use mono-fold-left to sum up all the elements, right? Now that's very interesting, because it means that if we can transform a parList of samples into a parList of temperatures, then the problem is solved. Do we know a function that transforms every element inside a parList? Yes, we do. It's map. So let's do this. We're going to take our samples here, and the first thing we'll do is to call map on this. So we'll have a sample, and we extract the temperature out of it. Let's do sample.temperature Fahrenheit. This gives us a parList of double, and now, if we want, we can squash all those doubles together using mono-fold-left. So this will require a monoid of double, right? Let's have a look at monoid. So far we only have a monoid of int that sum the ints together. But it should be relatively straightforward to do the same for double. So what we can do is even copy-paste this monoid, and let's call it a sum double. And then every time we have an int here, we'll replace it by double. So default return a double, and combine takes two double, and combine them together. Actually, the implementation is the same. We can put 0.0 just to make it clear that this default value is a double. So now let's try to run a test to verify that sum double is a valid monoid. So let's go back to our parList test. And last time we implemented this function checkMonoid that lets us run a test, property-based test, to verify if a monoid is a valid instance. So here we just need to add one line of code that says sum double, and we really let SkyCheck to do the hard work to verify that sum double is a valid monoid. So let's run the test. Cool, it passes. But if we run this test suite in our continuous integration platform, it will eventually fail. This is because double has limited precision. Instead of waiting a couple of days for a failure to occur, what we can do is tweak SkyCheck configuration so that it tries to invalidate the property in a more rigorous way. By default, SkyCheck considers that a property is successful if 10 iterations of the test are successful. But we can change this by overriding a variable called generator-driven config. Let me show you. So what we can do here is say, please override a method. So it's called generator-driven config, this one. So it's a weird combination of keyword and override implicit. To be honest, I think only Ch03 does such a thing, so I'm not going to go into the detail. But really the important bit is this property check configuration. So let's open it. So property check configuration is the object that configures how do you run property-based test inside of Ch03, the testing library that we use. And as you can see, by default, it requires 10 successful evaluation. So what we can do here is just generate the default configuration, but change it to say that, or just change mean successful, and say, let's say 10,000, just to be sure. And let's rerun the test. As you can see, the test took much longer to run because we had to generate more random values. But now the test fails almost every time we run them, which proves that sum double is not a valid monoid. Let's have a look at the counterexample that Ch03 gives us. So for example, we can copy-paste these values here. So what Ch03 tells us is that if we use these three doubles, and we sum them together using different placement for the parentheses, then we get different results. Sometime we get this one, sometime we get this one. So what we can do is, just to make it sure, we could pop up a REPL, so just to run some code, to evaluate some code in the command line. And so let's put these three numbers together. So the first time we're going to evaluate the first two doubles like this, and then we'll reevaluate it, moving the parentheses around. So as we can see, when we put the three numbers, when we put the parentheses this way, we get this double here. And if we move the parentheses like that, so if we first combine the last two values and then combine the first one with the last two, we get something slightly different. So here we have two options. Either we change the temperature encoding from double to a type with an exact representation. For example, one coming from the numeric library Spire. Or we could simply accept that when working with double, there is a certain level of inaccuracy, which means that PARList may produce slightly different results based on the way the data is partitioned. In my opinion, it's fine to use double because we are dealing with temperature data with a very limited range, so it's extremely unlikely we'll face this issue. So the only thing we need to do here is to constrain the random generator for double. So let me show you how we can do this. So what we want to do here is to define a new random generator for double. So it needs to be, so it's called a double arb. So this is an arbitrary of double. As you might remember, arbitrary is a random generator type used by Ch03. And it needs to be an implicit because this is the way we pass the random generator in our test. So how do we define it? Well, we create a gen and we use the choose function that provide like lower bound and upper bound. So we can say, let's say, between -100 to +100. Cool. Let's rerun the test. So the test still fails, which shows that addition is not associative with double, even for small numbers. So let's have a look at the counterexample. Once again, this is a problem of precision. The numbers generated by Ch03 have too many decimal places, which cause rounding issues. We can see it here. We need to constrain the random generator so that it only generates numbers with fewer decimal places. One way to do this is to ask Ch03 to generate floats and then convert them to double. This should work because floats are encoded with 32 bits, while double use 64 bits. We can generate floats by adding a letter F after -100 here and +100. So now this is going to be a gen of float, and we can change it to a gen of double by using map and use the method toDouble to upcast the float into a double. Let's rerun the test. Great, so now the test passes, which shows that double is a monoid as long as we don't have too many decimal places. One thing I don't like with this definition of a random generator for double is that we use the implicit keyword, the fact that we pass this random generator implicitly. Why I don't like that? Because it's not clear where it is used. For example, we can't use our IDE to tell us that where is this value used. You know, as you can see, IntelliJ tells me there is no usage for this double. So the only thing we can know is that to carefully read each line of code, and this is very error prone. So that's why I would suggest to, instead of passing this random generator implicitly, what we can do is pass it explicitly. So meaning that here we will have a gen. So because gen is a random generator we use when we pass it explicitly, so we'll remove this constraint. And now we slightly need to change our test, because when you use gen, you need to manually pass it to for all. So we need to pass it once for each time it is used. So it is a little bit more verbose. But I think we'll gain in readability and it will be much easier to understand. So let me show you. Now what we're going to do is that we'll change this value to be a gen, not an arbitrary, and we don't need the implicit keyword anymore. And now, okay, so that's good. And we'll pass this random generator for double explicitly to check monoid. Now we need to do the same with some int, so we need to generate a random int. But for int, we don't need anything special. We can just generate any kind of value that exists. So we can say choose between int min value and int max value. And then we pass it again explicitly to check monoid. Let's run the test again. Cool, so the test passes, we haven't broken anything. And now the nice thing about this approach is that we can now use our IDE to say, could you please tell me where this random generator for double is used, and it will tell us that it's used in only one occasion in this line, that when we check this particular monoid. So I think this way the code is much clearer. Okay, so let's come back to the exercises file and review our implementations. Actually, we didn't fill this one, so we need to say that this needs to be a monoid of some double. So it turned out that what we did here is that we reinvented MapReduce. We can't implement fold left on several partitions, but nothing prevents us from achieving the same result by first mapping the dataset to the expected type and then reducing it all together into a single value. Okay, so let's apply the same process to size. Please pause the video and have a go at refactoring size. Okay, so we'll use the same technique. First, we take our samples, then we map it to the expected type. So we map each sample into a value of type int. We don't know yet how to do this. And then once we have this power list of int, we'll squash them together using our monoid SumInt that will add them together. Now the tricky part is to find out how to convert a sample into an int, so that monofold left calculate the size of the power list. If you have never worked with MapReduce before, you will probably find this difficult. One way to think about it is to ask ourselves, what should the function size return in case there is only one sample within the power list? Well, in that case, we would expect size to return 1, right? If there is only one element in the power list, the size is 1, it doesn't matter what is the value of the sample inside it. So this is exactly the map function that we need to implement. It doesn't matter what is a sample, for each sample we return 1, and then SumInt will add all these ones together to return the size. That's a bit weird, but that's how it works. So let's put an underscore here to just make it a little bit clear, and let's rerun the test. Actually, I'm going to change the configuration in parlist test to reduce it to 100 just so that we don't have to wait forever every time we run the test. Cool, so now all the test passes. So you probably find the map part of MapReduce the strangest, but it will get better as we implement more operation using the MapReduce pattern. As a side note, size is completely generic. It doesn't matter if the content of the parlist is a sample or something else. So what we could do is first make size generic by using a type parameter. And even better, what we could do is move size inside of the parlist class so that it will be much easier to use. So here we can say actually size is just map followed by monofold left. So we might have broken a couple of tests by doing so. Let's rerun them. Yes, so here, as you can see, before we used to do size of numbers. Now it will be much nicer. We'll say numbers.size. So it will really be like all the collections. Let's rerun the test. All good. Now that we have re-implemented sum temperature and size using monofold left, let's see if we could apply the same refactoring to average temperature. So let's go back to this. Currently, average temperature has a rather convoluted implementation, because our aim with this version was to calculate the temperature and the size in one iteration. Take a few minutes to pause the video and try using map and monofold left to re-implement average temperature. Cool. So what we want to do here is really change this line of code. At the moment, this is the current hand-rolled folding logic that we implemented that is quite boilerplatey and error-prone. So ideally here, we want to replace this line by map followed by monofold left. So what we want to do here is to take our samples. First, we map it. So we map it to which type? This is going to be the type that we expect to return at the end. So this is a double and this is an int. So we need to have a tuple, a double int here. So this will be the map part, and then we need to fold them together using monofold left. So here this means that we need a monoid of type tuple double int, right? So this will be the shape of the MapReduce. How do we implement map? So again, we need to think what should average temperature return in case there is only one sample in the list. So in case there is only one sample in the list, what is the total temperature? Well, it is the temperature of this particular sample. So we can just say sample.temperature Fahrenheit. And if there is only one sample in the par list, what is the size of the par list? Well, it's 1. It's exactly like what we did for size. So that's it. We now have the map function. Now we need to implement a monoid that, given a tuple double int, sum them together. So it's probably going to be very similar to the code we wrote here. So let's say sum double int, and this is going to be a monoid double int, right? Now, the implementation, so what is the default value? Well, it's the same as before. It's basically 0, 0 or 0.00. And here it's a bit annoying. So here we have the first value is a tuple, the second value is a tuple, and we want to sum all the doubles together and all the int together. So how do we do this? Well, we do first dot _1. So _1 is a value is a function on tuple that gives us access to the first field, and same with second. So we take the first value of first and the second value of first, and we sum them together. And basically we do the same with _2. We take the int from the first and the int from second, and we sum them together. So it's a bit boilerplatey. We'll see later how we can refactor it. And now let's try to verify that this, so yeah, what we can do first is now replace this monoid here sum double int. And we can rerun our test because we already had some tests for average temperature. So we'll see if we haven't broken anything. Everything works. Now another thing we want to do is to verify that this new monoid we implemented is a valid monoid. So we can say sum double int, and here so this means that we need to have a random generator for a tuple double int. How do we create such a random generator? So if we look at the Jane API, there is a function called zip that if you pass two random generators, one for T1 and one for T2, it gives you back a random generator for T1, T2, so a tuple T1, T2. So this seems exactly like what we need. So here what we want to do is to say, okay, first let's generate doubles using the custom double generator we developed, and use the default int generator. Let's rerun it. Cool, it all works. Now we could come back a bit to this code because it's very annoying to have to write such a monoid that seems almost automatic. It seems that we basically took the monoid for double and the monoid for int, and we kind of zip them together, very similar to this zip method in SkyCheck. So could you please pause the video and try to implement such a zip method? So I will write the signature for you. So zip is going to be something that takes a type parameter a and b and takes two monoids, so a monoid a for monoid of a and a monoid b for as a second parameter, and hopefully what we want to generate is a monoid of a and b. So could you try to write zip, test it, and refactor sum double int using zip? Okay, so what we can do here is copy-paste the code for sum double int, and here we'll just generalize it in zip. So every time we saw a double, we'll use a, and every time we had an int, it's going to be a b now. Okay? Now what will be the default value? So here we need to return an a, so we can take the default value from monoid a, and here we need to return a b, so we can take the default value from monoid b. Quite straightforward. Here we want to combine the first item of each tuple, and so they are both a. So the only way we have to combine a is to use monoid a. So we'll say monoid a.combine, and here we'll, instead of using plus, basically we use the combine function passed as an argument. And here we'll do the same for monoid b. Let's see if it compiles. Yes, it does. So one thing I really like about using a more generic version like zip is the fact that now this is actually safer. So for example here, let's say we were going to combine the first value of first and the second value of second. Now it will not compile because monoid a combine expect two a's, and this one is a b. So the compiler will tell us you can't do that. While here, when we were combining a double and an int, it's very simple to do this, to sum the first double with the other int, and this will compile because you can sum double and int together. So the generic version is safer in that sense. Now we can re-implement this very easily. We say it's just zip of sum double, sum int. On top of that, this should simplify testing, because here, instead of having this sum double int test, we can generically write a test for zip that says, if you pass me two monoids, and here the key thing is that it doesn't matter which monoid it is, because zip is completely generic. It accepts any kind of monoid. So if it works for some int, it will work for any other monoid. And here we can use a simpler generator. So now this way we can have a single test for zip that is simpler than the one before. We don't need to use our custom kind of complicated double generator. And yeah, it all works. Okay, so let's go back to average temperature. The code is much simpler now, and we can get rid of these old hard-coded folding functions. We also discovered that we can easily zip multiple monoids together, which allows us to run several computations in one iteration over the dataset. This is going to get very handy. Now, there is just one issue comparing to the previous implementation of average temperature. We need to iterate once over the dataset to transform it into the desired type, and another time to reduce it all the data. Whereas with the previous algorithm, we were able to do it all in one go. This may not seem like a big difference, but if we have millions of data points, it can get expensive. So is it possible to do better? Is there a way to map and fold in one iteration? And if not, is this a limitation of the MapReduce model? Please pause the video and try to think about it for a few minutes. So what we can do is go to our Police class and define a function, for example, let's call it MapReduce, because it captures the MapReduce pattern. So we want to have an update function that will transform every single value inside the dataset into a 2, and then we need a monoid of 2 in order to squash all these values together. And this will return a 2. Yeah? Okay, so now one way to implement this function is really to do map with the update function, and then to do monofold left, passing the monoid. So it's exactly the same as we have done before, but the nice thing with implementing this function is that we capture this pattern, and then if we can make it more efficient, then all the other implementation will benefit from it. So what we can do now is to refactor all these methods to use MapReduce instead. So we have size, here we have average temperature, and what else do we have? We have some temperature as well. Actually, we can simplify the implementation slightly and remove monofold left here. Cool. So we haven't changed anything. Actually, let's rerun the test just to verify it. But now the nice thing is that we do have this function MapReduce inside of the Police class. And now our goal is to try to make it more efficient, to try to implement MapReduce in one iteration over the dataset. So if you haven't implemented this function yet, could you please pause the video and try to do it now? Okay, so what we can do is actually copy-paste the code from monofold left, because this is the most complicated part. This is the part that, fold all the data together. And as we can see, we have a problem here because the combine function is not matching. But it's not necessarily clear what is exactly the problem. So what we can do is just to expand the code a little bit and introduce variables so that, we understand a little bit more what is the issue. So here, let's call it partition. And so now here we do a fold left. So this needs to be a state and needs to be a value. And then you pass, so state needs to be of type 2 because this is the value of the default from the monoid. And value is whatever is inside of the Police. So this is an A. And before we were passing state and default and value like this. So now we can see this is much clearer. Now IntelliJ tells us that value here is of type A, but what we need is something of the same type as this monoid, so it's something of type 2. So if we were able to transform this value from an A to a 2, then the problem will be solved. Well, we can do this because we have an update function here. So let's apply this update function on value, and that's it. Let's rerun the code. Let's run the test just to check. All good. So we haven't broken anything. Now size, average temperature, all use MapReduce, that is a more efficient version than before, where we were previously mapping and reducing. Now we do all in one go. As a side note, this function normally in functional programming is not called MapReduce, but foldMap. So let's rename it just for consistency. It implements the MapReduce pattern, but it's generally called foldMap. I'm not entirely sure why, but I have an idea. So in fact, we do map and then we fold. So you could think that it should be called map-fold instead of fold-map. But in traditional functional programming, we don't use the OOP syntax. So we do something like fold, and then inside of the fold, we map. So I think that's why in traditional functional programming, it would be encoded like this, which means that it's called foldMap. It's the same way that you call flatMap when you do map plus flatten. At least that's my guess. Now, how do we test foldMap? Well, we already have it tested because we have many functions using it. But we could also write a test that verifies that foldMap is consistent with map plus fold left, plus monofold left. So we could say foldMap is consistent with map followed by monofold left. So I'll let you pause the video and try to write such a test oracle. Okay, so what we can do here is we need to call, so this doesn't necessarily need to be a par list of int, it could be a par list of anything. The only thing is that we need to call foldMap on it. So here we need an update function. So for example, this could have been a string, and we need an update function. So scancheck is very well able to generate random function. So we can say this needs to be from string to int here. And then we need a monoid of int. So it would be nice to have a random generator of monoids. Actually, in the advanced exercises at the end, I added a question for this. But for now, we can just pass it explicitly. So we can say sumInt. If we want, just to make it easier for later for refactoring, we can say that we actually don't really care about what is a monoid. We just need one. So we can say here monoid. So this is going to give us an int. And we want to verify that this should be consistent from using first map and then monofold left. So here really what we verify is that our more efficient implementation of foldMap, the implementation that does everything in one iteration, return exactly the same result as if we were doing in 2 steps. So let's run the test. All good. Now you see that this test took a little bit longer to run. I imagine that it's because the generating function is probably a little bit more expensive than the rest. So we can see it took 432 milliseconds, while this one took 126. So it's always good to have like snappy tests in our continuous integration. So how could we improve it? Well, you might remember from the previous chapter, we said that when we were testing map, we actually don't really care about the update function because of generic functions. We know that the update function must be called because at the end, this will return a value of type 2, and the only way to get a value of type 2 is to use the update function. There is no other way. So we know that the update function will be used on every single result. So instead, what we can do here is drop this update function and say, okay, let's generate a par list of int, which is simpler. And let's test with the identity function, which is the simplest function possible, a simple update function. Let's rerun the test. Cool, it works, and it was a little bit faster. Now it took 68 milliseconds, which is much better. We can actually even do better than this, because when we have map with the identity, it does nothing. So we can say that actually foldMap with foldMap identity is consistent with monofold left. So we do the same test, but thanks to generic functions, we were able to optimize the test and have something that actually covers the same ground. Awesome. Now we have a simple and efficient implementation for average, size, and sum. It took us some time to get there, but it was worth it. That said, there is still one method we haven't converted to full map. And I think it's a min sample by temperature, the first function we implemented on parlist. So could you please pause the video and try to refactor min sample temperature to use a full map. Okay, so we know that we want to call full map on samples. So this means that we need a function that converts a sample into the output type. So it needs something into an option of sample. And we need a monoid of type option of sample. So this is the two things that we need in order to use the MapReduce pattern for calculating the sample with the smallest temperature. So first, how do we do the update function? So again, we need to think, what should min sample by temperature return in case the parlist has only one element inside it? So imagine this is a sample, the only sample inside of the parlist. What will be the min sample temperature in that case? Well, it will be this one. If there is only one sample, it is the minimum and the maximum. So we can wrap it inside of a sum and say sum sample. Now, the problem with sum is that we had this issue before with folding when the type inference will infer a type that is too precise. This is a current issue with Ch02. So actually here we can see that here it says that we provided a monoid of option of sample, but it wants a monoid of sum of sample. This is because we specified sum here. So actually what we need to do is to upcast this value and say that actually this sum of sample need to be an option of sample. This is what we want. So it's a bit of a hack, but we have to live with that for now. Okay, so we can even simplify this function and say, okay, what we want to do is that for each sample, we just want to wrap it in an option. Essentially, that's what we want. Now, we need to write a monoid here that this monoid will figure it out what is the min sample. So let's call it min sample. And this will be a monoid of option of sample. So how do we implement this? So the default value. Default is going to be what we return in case there is no value inside of the parlist. So if there is no value inside of parlist, the minimum value is none. So combine is the interesting bit. So we have two options of samples. So this is like, maybe this is a minimum value, maybe this is a minimum value. Could you please figure it out which one is the smallest among this one? So what we need to do here is to pattern match on both of them and do something. So there are four cases. Either they are both none, either they are both sum, or one is sum and the other is none. So let's make it clear. So the first case is none, none. And then we have, in case we do have a sample on the left, in case we do have a sample on the right, in case we have a sample on the left and a sample on the right. So now let's do it one by one, sample 2. If we have no sample on the left or on the right, then in this case, the minimum sample, there is none, there is no sample. If there is one sample on the left and none on the right, then it's basically it's this sample. Same here. So actually the first three cases are really stupid, like you don't really need to think much about this. So the last one is the only interesting one where we say, okay, we do have two samples. Can you please figure it out which one is the minimum value? So what we need to do is say, if sample 1 dot temperature Fahrenheit is lower than sample 2 temperature Fahrenheit, in this case it means that sample 1 is the minimum value, so we'll return it, sum of 1. Otherwise, we'll return sample 2. Yeah? Let's verify that this is a valid monoid. So we could write our parlist test. So we'll say min sample. Could you please verify that this is a valid monoid? And here we need to have a random generator of option of sample. So gen has a method option that if you give it a random generator of A, it will give you back a random generator of option of A. It will basically wrap some of the A into a sum. So some of the sample, it will put it in a sum, and sometime it will generate a num. So here, the important bit is to get a random generator of sample, but I define one in the parlist test instances we've seen before. Okay, and the last part is that we need to replace the monoid here. So we need to use min sample. So let's run the test. All good. Now all the data analysis functions we have written on parlist are implemented in terms of format. This is awesome because the code is much easier to understand and to test, since most of the logic is encapsulated in the monoid. Additionally, the code is also efficient, as fullmap iterates a single time over the entire dataset. Even better, if we find a way to run fullmap in parallel, then sum, min, and average will also run in parallel automatically. So let's take a break now, and in the next video, we'll finally introduce parallelism to parlist. See you soon.